All right. Hi, everyone. Welcome to our project presentation. I am Violet, and today I'm presenting together with my teammates, Kim, Ancho, and Maya. And our project leads are Akshay and Samir. Our engagement lead is Linda, and our data scientist is Wang. So let's talk about water. We are in contact with water every day. We drink water, we bathe with water, and we engage with water activities, especially for folks in Seattle during the summer. But water is also an integral part of our lives in ways that are often hidden. We use water to generate power. We use water to grow agricultural produces, and we use it to produce microchips that are carried in our phones and laptops. We use water in so many ways, but only a small fraction of the total water on Earth is fresh water that we can use. This water exists as surface water stored in streams and lakes above the land surface, as snowpacks, often found on mountaintops, as moistures in soil, and groundwater, which is the focus of our project. So what exactly is groundwater? Groundwater is the fresh water stored in the ground beneath the Earth's surface in the saturated zones, as pictured on the slides here. So imagine a sponge soaked with water. In this case, the Earth in the saturated zone is a sponge, and water from precipitation and other sources travels down from the surface and gather in the saturated zone, where all the pores between rocks and soils are filled with water, and this becomes groundwater. Groundwater is an extremely important source of water. Over half of the US population relies on groundwater for drinking, and this number goes up to nearly 100% for rural communities. And arid communities are especially reliant on groundwater, and people extract groundwater by pumping them through the wells that are shown in the slides. So in the US, groundwater is used for over 40% of irrigation and provides more than 60% of the water used for livestock purposes. Groundwater also plays an important role in the hydrological cycle. It contributes to the flows of rivers and streams and lakes that are habitats for plants and animals. The time it takes for groundwater to replenish varies, but it can take thousands of years, making groundwater an absolute critical and scarce resource. Even so, groundwater has been largely out of sight, out of mind in many water management practices due to its lack of visibility and the difficulty in measuring groundwater. This means that in some places, people could be taking more groundwater than it can replenish, which could have a number of consequences, such as reduction in agricultural yield and land sinking.
Okay, so I want to now turn to discuss water scarcity, which is when demand for fresh water exceeds the supply of fresh water. So more specifically, it refers to the situation where there's an insufficient amount of clean and safe water available to meet the needs of a specific region's population. So as you can see from the map on the right, water scarcity is a global problem with many countries projected to have high or extremely high water stress levels in 2040. So water stress is defined as the projected ratio of water withdrawals to water supply. And many of the countries, as you can see on the map in the mid-latitude area of the globe, are projected to have high or extremely high projected water stress levels. So some key drivers of water scarcity across the globe include climate change, population growth, pollution, and inefficient water management practices. So the Colorado River Basin is a more specific example of an area that's facing significant water scarcity. So on this slide, you can see several news headlines from the last few years highlighting the severity of the problem within the region. So a few key points that I really want to emphasize here on this slide, that the region saw its first ever water shortage in history declared. Drastic cuts to current water usage must be made in order for there to be sustainable management of the river, and climate change, inequitable water distribution, and demand growth are key drivers of water scarcity in the region. So where and what exactly is the Colorado River Basin? So the Colorado River Basin, as you can see on the slide, is a large area in the American Southwest surrounding the Colorado River, spanning 7 US states, 2 states in Mexico, and 30 tribal nations. So as you can see on the map, it's divided into upper and lower basins at Lee's Ferry, and this is as a result of historical agreements in 1922 among the Colorado River Basin states. So these agreements mandated that the 2 basins equally share water and focused on surface water management primarily, and this is a focus that has stubbornly persisted today. So the upper basin, with its more mountainous region, contributes much of the water to the Colorado River Basin from melting snowpack each year. So the river is economically, socially, and culturally very important. It serves 40 million people. Sorry about that. Serves 40 million people, provides irrigation for 5.5 million acres of land, and supports close to $1.5 trillion in annual economic activity. So despite its importance, groundwater has largely been left out of policy decisions in the Colorado River Basin. So as previously mentioned, this is partly because of some rigid policy structures that were put in place as a result of these 1922 compacts. And another key reason is that it's because groundwater is less visible and can be difficult to measure. So historically, people have relied on well measurements, which are expensive and result in less frequent measurements. So more specifically, these measurements require first constructing a well, which is in and of itself expensive, then installing a measuring mechanism, and then collecting, analyzing, and storing data. So the measurements are limited to the frequency at which measurements can be taken and the locations of the wells themselves. So I want to point now to the right-hand side picture here, which shows a bathtub ring at Reflection Canyon in June 2021 in Lake Powell. And really emphasize here the surface water component, which has largely been the focus of a lot of previous policy decisions. So as mentioned in the slide, the 2007 interim guidelines were a set of guidelines established to manage water during drought and water scarcity in the region. And these guidelines focus primarily on surface water management. So they don't give guidance for how states should manage groundwater. And they're set to expire in 2026, making information on groundwater particularly crucial. So turning now to just sum up what we have so far. So groundwater is a crucial freshwater resource. It's often been ignored in policy decisions and political contexts. Measuring groundwater has also historically been expensive, infrequent, and confined to well locations. And water crises are becoming more commonplace in the US and across the globe. So sustainable water, and especially sustainable groundwater management practices, are essential. And to put it simply, you can't manage what you can't measure. And so our project, using data from NASA's GRACE mission, can help fill this groundwater gap.
So what exactly is this GRACE mission? As technology advanced, NASA, in collaboration with the German Space Agency, launched 2 satellites in space in a mission named GRACE, which stands for Gravity Recovery and Climate Experiment. In this mission, these satellites, separated by 137 miles apart, orbit around the Earth to detect changes in Earth's gravity fields using GPS and microwave ranging systems. These satellites measure changes in the pull of gravity, which refers to how water is shifting around the Earth due to changing seasons, weather, and climate processes. By measuring gravity changes, GRACE showed how mass is distributed around the planet and how it varies over time. Data from the GRACE satellite serves as an important tool because after doing modeling and statistical analysis, you can calculate the entire water that is stored on the Earth. And if you combine it with other data sets like we did, you can also calculate groundwater in every other region of the Earth. So to calculate groundwater, there are different components of water that are required. So we have talked about total water storage that GRACE can give us, but there's also other components like soil moisture, snow water, and surface water. We can derive soil moisture and snow water from GLADYS, which is a data set which stands for Global Land Data Assimilation Systems. And then there is surface water from reservoirs, which we can get from USGS, which stands for United States Geological Survey, and USBR, which is United States Bureau of Reclamation. But the process to compute groundwater is complicated. To use any data, there are 3 steps that are involved. You have to download the data, you have to process the data, and you have to be able to interpret the data. There are challenges involved in every step with these data sets. So in order to download the data set, if you just search the word GRACE on NASA's Earth Engine, there are 145 matching data sets with that search. The GLADYS, which contains the soil moisture and snow water, has monthly measurements, daily measurements, hourly measurements, but you would need probably yearly measurements of soil moisture, snow water. That ends up being like 10,000 plus files for only 1 year. There are also multiple variables in a single file. And for processing these data sets exist in different units, resolutions, frequencies. They also exist in a geospatial format, which many social science researchers are not used to. Finally, even if you can download and process these data sets, understanding these data sets is another challenge. The numbers are present in changes rather than fixed numbers. So basically what I want to highlight is that there is zero detailed guide to calculate groundwater for non-experts. So this is where we come in. Our contribution is that we built a flexible and well-documented workflow that can easily be used to study groundwater changes in the Colorado River Basin and other regions. One of the primary objectives of this project is to establish clear and effective documentation accessible to our project leads, as well as researchers of varying technical background. The aim is to produce reproducibility of the workflow beyond what we have achieved here in these 10 weeks. And to do so, we have created Markdown files and notebooks, which are available on our website and updated on the GitHub repository, which ensures widespread access and availability. We have also created our workflow thinking about our potential users and interested groups. Our primary potential user are the researchers. We believe that our workflow can help them increase their efficiency in allowing them to understand the study of groundwater more effectively. We also believe that our secondary users are policymakers, advocacy groups, and general public. The insights that can be gained from the data used in our workflow can help distribute policymaking decisions, as well as about water allocation decisions, and could also educate the general public about water scarcity and groundwater changes in Colorado River Basin. Now I'm going to talk a little bit about the workflow that we have created. So our workflow consists of multiple Markdown files and codes. And basically, these are the steps that our workflow consists of. It helps you find the right data set of interest. It helps you download the data of interest, as well as process the data, apply the equation which is needed to compute groundwater, and finally visualize the trends.
Okay, so I'm going to walk you through some example outputs of our workflow and highlight the types of questions that you can answer with these outputs. So say that we have a researcher named Martha. Now she lives in the Colorado River Basin, specifically in Arizona, a state that relies heavily on groundwater. Now she has some technical chops and she's interested in how groundwater moves and how it can be computed. So in order to calculate the change in groundwater, she'll need several variables. So the first is terrestrial water storage, as mentioned previously. This is the summation of all water on Earth. Now, the next one she needs is snow water equivalent, which is the amount of water available in snow that is packed in areas such as mountains. She'll additionally need the root zone soil moisture, which is just the water that is available to plants underground. And then finally, she needs surface water, which is the water found on Earth's surface that we can easily see, such as within our rivers and within our ponds. Now, you'll notice that we say changes or anomalies a lot, like mentioned with Grace. But that can be a little confusing, so I'll walk you through it. So if you look at the graph here on the left, we have the raw data graphed in gray, and then the mean over this time series is graphed in pink. Now, if you compute the distance for each point in the raw data from the mean and plot those points, then you get deviation from the mean. And that is the form that our data is in. So Grace doesn't measure the total or absolute water storage, but rather you think of it as mass changes. And so we typically don't know the value that it's changing from, and so we create a reference point. And so using the equation mentioned previously, I'll walk through some examples of the figures that Martha, the researcher, might produce. I want to note that these are preliminary analyses, and so we're still in the process of validation. Now, this slide shows a plot of groundwater anomaly in the Colorado River Basin over time. The x-axis is time, and the granularity is in months, while the y-axis is groundwater volume in kilometers cubed. And 1 kilometer cubed is just over 400,000 Olympic-sized swimming pools. So that gives you a sort of idea of the scale of water that we're dealing with. And so aside from the seasonal and annual trends that you can see, we additionally observe a downward trend starting just after 2012. Now, even when we compute a 12-month moving average to eliminate these annual trends, we can see that groundwater does continue to deplete over time. And such a plot could bring out a sense of urgency for a researcher like Martha. Now, as mentioned previously, our groundwater anomaly plot is averaged over the entire Colorado River Basin. But using our workflow, a researcher can look at a specific point in time over the entire basin. Now, for example, in October 2003, we noticed a significant drop in groundwater. We can look at the spatial distribution of the groundwater anomaly for a singular point in time. And that makes sense why the point is so low, because we see so many red values. Now, conversely, we can take a look at a very wet month, such as May 2011. Now, we observe higher groundwater storage in the upper basin, which makes sense because the area is more mountainous. And then we see that the lower basin does remain drier even during a wet year, which makes sense because the lower basin is more desert-like. Now, speaking of the upper and lower basin, we can, using our workflow, look at individual basins and their trends over time. Now, the division between the basins was decided politically, but it turns out that the upper basin is a crucial water source for the lower basin. And so we observe that even though there is still this downward trend over time for both the upper and lower basin, it's more significant within the lower basin. So Martha went from all of this complicated data to digestible figures that she can draw conclusions from. And now Martha, armed with this and new information, can empower individuals within her community to advocate for sustainable groundwater practices and policies. Now, unfortunately, the Colorado River Basin is not unique in that it's facing significant water stress. As mentioned previously, these crises are happening all over the world. So just a few examples, the state of Bihar in India is experiencing decreased rainfall and decline in groundwater levels. And the country of Egypt in Africa will have very exacerbated water crises in the very near future. And so we hope that our tool can empower researchers across the globe. And so in summary, the two takeaway messages we really want to drill home are that groundwater is important, but extremely hard to measure. And our workflow thankfully simplifies this process to study groundwater. If you want to find out more about our project, you can visit our website linked here. And not only is there more information about the background and the motivation, but also access to our GitHub, which has detailed workflow in the form of notebooks and markdowns. And we're working to have this finalized by the end of the week. And we want to say thank you to so many people for help and support throughout this project.